Hi everyone, my name is Rohan Singh Poona and welcome back to my channel. In this video, we'll be learning something called as Master's Theorem for divide and conquer algorithms. So let's get started. Before we jump on to Master's Theorem, let's try to understand in basic terms what is a divide and conquer algorithm. So let's see what are divide and conquer algorithms. So all divide and conquer algorithms are nothing but they divide the problem into subproblems such that each of which is a part of the original problem. And then we perform some additional work to compute the final answer. One basic example that I can give you is merge sort. Now merge sort is an example for divide and conquer algorithm. Now in merge sort, we are required to sort an array. So we are given an array which has n elements and we are required to sort this array. Now what merge sort algorithm does is, it assumes, let's say, if somehow we can get the first half of the array as sorted and let's say the other half of the array as well as sorted, then we can merge these two sorted arrays to achieve the finally sorted array. If we can get these two halves sorted, then we can merge these two halves and get the final sorted array. Now, if we try to find the time complexity to sort n elements using merge sort, then we can see that it can be the time taken to sort this first half and then the time taken to sort the second half. So I can write it down as t of n by 2, which is nothing but time taken to sort the first half plus time taken to sort the second half plus time taken to merge these two halves, and that takes big O of n time. Therefore, as you can see, t of n by 2 plus t of n by 2 will be nothing but 2t of n by 2 plus big O of n. So this will be the time complexity for merge sort. Now I hope you got a basic understanding of what are divide and conquer algorithms. So I'll just summarize it again. So as a part of divide and conquer algorithms, we tend to divide the problem into multiple subproblems and we solve those subproblems, and at the end we tend to perform some additional work on those solved subproblems to achieve the final answer. So that is what is a divide and conquer algorithm. Now let's get back to Master's theorem. So as you can see, just by looking at this particular Master's theorem, you might feel, there is a complex equation. It says, it uses a big words in the theorem like recurrence relation of the form, this and this, some real number, something, right? So it's not that complex, but let's try to break this first. There's something called as recurrence relation. So a lot of you might be knowing something called as recursion, or you might be already knowing what is a recurrence relation. But let's try to first, get a basic understanding of recurrence relation. And then we can, get back to again Master's theorem. So let's see what is a recurrence relation. So recurrence relation is nothing but it is a mathematical concept which is a part of discrete mathematics. Now let's try to understand what is a recurrence relation further. So it's nothing but an equation according to which the nth term of a sequence of number is equal to some combination of the previous term. So let me break this down for you. One example can be, let's say if we have to find n factorial, then I can say that n factorial is nothing but equals to n into n minus 1 factorial. So now n is nothing but equals to n minus 1 factorial. So as you can see that the n factorial depends on previous term, right? As it says, nth term of a sequence of number is equal to some combination of the previous term. Here the combination is nothing but we multiply n with n minus 1 factorial, which is the previous term in this case. So if we have to write the time complexity to find n factorial, then if t of n is the time complexity for computing n factorial, then I can say that it will be equal to, we are applying one operation which is nothing but here the multiplication operation. So let's say that takes 1 unit of time, plus we ideally are also computing n minus 1 factorial. So if t of n is the time taken to compute n factorial, then t of n minus 1 is the time taken to compute n minus 1 factorial. So this will be the time taken to compute n factorial. Now here, as you can see, t of n depends on t of n minus 1, or you can say that the nth term is nothing but equal to some combination of previous term, which is here t of n minus 1. And this is what is a recurrence relation. The above equation is also a recurrence relation, and this equation of time is also a recurrence relation. Now, as you can see this equation, t of n equals to 1 plus t of n minus 1. If you break this equation down further, then t of n minus 1 will also be equals to 1 plus t of n minus 2, and t of n minus 2 will be equals to 1 plus t of n minus 3, and so on until this n minus 1 becomes nothing but either 0 or 1. Now it depends on, like what's the base, what's the last element. We can say that 1 factorial is 1 factorial, 0 factorial is 0 factorial. So it will go till 1, and it can also go, let's say, till 0, right? So if we actually try to sum up all of these, then the time complexity here will be nothing but equals to big O of n in this case. Yeah. So I hope you got a basic understanding of what is a recurrence relation. It is nothing but, it is an equation apparently in which the nth term of a sequence is nothing but equal to some combination of the previous term. As we saw here, n factorial is equals to n into n minus 1 factorial, or we can say t of n is equals to 1 plus t of n minus 1. Cool. So let's get back to Master's theorem. Now Master's theorem says that whenever we have a recurrence relation of the form of this form, t of n equals to a t of n by b plus big O of n power k log base 2n power p, where a is greater than equals to 1, b is greater than 1, k is greater than equals to 0, and p has to be a real number. Then, only then, there are three conditions in which we see that if a is greater than b power k, a is equals to b power k, or a is less than b power k. If a is greater than b power k, then t of n is simply big O of n power log base b a. If a is equals to b power k, then we have three subconditions and corresponding time complexities for all those three conditions. Same way we have the third condition where if a is less than b power k, then we have two subconditions and corresponding time complexities for both of them. Now basically Master's theorem can only be applied for divide and conquer algorithms. That's why I have mentioned this here, and it can be applied only to the recurrence relation which are of this particular form, t of n equals to a of tn by b and so on. Yeah. So a lot of you might think, whether Master's theorem is important or not, and whether it will be asked in interviews or not. So from the perspective of interviews, I would say it's not that important. It might be helpful for college students, who are studying time complexity for the first time. As I would say, as an engineer, as a computer science engineer, understanding and knowing this is important in a way, and it's purely for knowledge, for the purpose of knowledge, gaining knowledge, I would say. So yeah, so this is the template of Master's theorem, and this is what Master's theorem states. Let's try to solve some sample problems, and based on that, you'll be able to understand Master's theorems in a better way. Let's jump on to some sample problems. Let's take one first sample problem. Let's say the given time complexity is nothing but t of n equals to 3 of t of n by 2 plus n square. Let's say this is the recurrence relation that is given to us, and we have to compute the time complexity for this recurrence relation. Now let me also write down Master's theorem time complexity here, because it will be easier for us. Otherwise we have to go up and down again and again. So what Master's theorem states, t of n is nothing but has to be of this form, a t of n by b plus big O of n power k log base 2 n power p. So now in this equation, if we try to compare this equation with the Master's theorem equation, we can agree that it is of the form which Master's theorem states. Therefore, by comparing these equations, we can get our a as 3. So a equals to 3, and this is nothing but b equals to 2, and as you can see, n power k, it has to be n power k, therefore k equals to 2, And we don't see anything, which is similar to log power p base to n, right? So as you can see, if there's nothing beside n square, we can always have into 1 here, right? Therefore, I can say that this one is nothing but log base 2 power p n is equals to 1. And this whole thing will be 1 only if when p is equals to 0. That is, a power 0 equals to 1. Therefore, in this case, Rp is equals to 0. Now, as master theorem states, if the equation or recurrence relation, given recurrence relation is of this form, then we need to compare a and b power k. Now, if a, in this case, as per this case, it is 3. Now, b power k is going to be 2 power 2, which is nothing but 4. Therefore, as we can see, a is less than b power k in this case. Therefore, as we can see, a is less than b power k. Then the condition which will be applied here is going to be the third condition. Now there are two subconditions which checks whether p is greater than or equal to 0 or p is less than 0. So as we can see, Rp in this case is equals to 0. Therefore, the first subcondition will be applied, and it says that the time complexity will be equals to n power k log n power p. So as per that, it says that big O of n power k log n power p. Now we know that p equals to 0 in this case and k equals to 2. Therefore, it will be big O of n power 2 log n power 0, which is nothing but big O of n square. Therefore, here the time complexity in this case will be equals to big O of n square. I hope this is clear. Let's jump on to the second problem. Let's say the recurrence relation given to us is nothing but t of n equals to 4t of n by 2 plus n square. Now again, we can quickly compare a, b and n, and here a equals to 4, b equals to 2, k equals to 2, p equals to 0. If we compare a with b power k, which is nothing but 4, and we can see that a is equals to b power k. Now if a equals to b power k, then we can see that the second condition will be applied. Now, as a part of the second condition, there are three subconditions which states if p is greater than -1, p equals to -1, p is less than -1. So we know that Rp is again 0 in this case. Therefore, it falls under first subcondition, which is nothing but p greater than -1. Then the time complexity will be equal to big O of n power log base ba into log n power p plus 1. Therefore, our time complexity will be equals to big O of n to the power log base b a. A is nothing but 4 in this case, which can be written as 2 power 2 into log power p plus 1 of n. So as we know that log base a equals to 1, and we know that log of, if it is base a power x, equals to x log base a. Therefore, I can say that this power will come down and this will become big O of n power 2 into log base 2 of 2 into log of p is 0 in this case, therefore 1n, which is nothing but big O of n square, and log base 2 will be 1. So n square log n. Therefore, the time complexity for this equation is going to be big O of n square log n. Let's take another example. Let's take third sub problem. Let's say we are given again t of n equals to 2t of n by 2 plus n by log n. Now if we try to compare this equation with the Master's theorem equation, do you guys think this is similar? Big O of n power k log base 2n power p. Someone might say, this is not similar because right here log is down. But as you guys know, we can actually take log up and have the power as -1. Therefore, we can rewrite this equation as t of n equals to 2t of n by 2 plus n into log power -1 n. Now we can compare this equation and find out the values of those variables. So we know that a is equals to 2, b equals to 2, k equals to 1, p equals to -1. Now if we compare a and b power k, therefore here a is equals to b power k, which is 2 equals to 2. Now if we get back to Master's theorem and see which particular subcondition is being applied, then we know that our p is equals to -1, which is nothing but the second subcondition. Therefore, t of n is equals to n power log base b a into log of log n. Therefore, our time complexity will be equals to big O of n to the power log base a, which is nothing but 2 in this case, 2 into log of log n, which is nothing but equals to, if we substitute log base to 2 will be 1, so in n log of log n. So this will be the time complexity in this case. Now let's look into another problem. Let's say t of n equals to 64 t of n by 8 plus n square log n. Let's say minus n square log n. Now you guys can pause this video for a moment and try to see if you are able to compute this time complexity or not. So I'll just count till 3 and you can pause. 1, 2 and 3. So guys, like here, if we try to compare this equation with the Master's theorem equation, then this is not, of the form which Master's theorem states. Master's theorem states that it has to be of the form a of t of n by b plus n power k, big of n power k, log power p of n and the base b, right? Yeah. So base 2, sorry, yeah, base 2n. So here, if you compare this equation, here we have, the function, has a negative sign here, but it has a positive sign. So this is not of this form, so we cannot apply Master's theorem in this case. We cannot apply Master's theorem. Master's theorem. Let's take another example. Let's say the given recurrence relation to us is 0.5 t of n by 2 plus 1 by n. Now again, if you actually try to compare this equation, then it might look similar to the recurrence relation which Master's theorem states, but here the value of a is equals to 0.5. Now if we look back to the Master's theorem, and the Master's theorem says that a has to be greater than or equals to 1. Therefore, again in this case, we cannot apply Master's theorem. We cannot apply Master's theorem. Same as previous question. Yeah. Let's jump on to another example. Let's say the recurrence relation given to us this time is nothing but 2t of n by 2 plus big O of n. Then if we actually try to find out a, in this case a is equals to 2, b equals to 2, k equals to 1 in this case, and p equals to 0. Now if we find a and b power k, so a is 2, b power k is 2. So as we can see, a is equals to b power k. Therefore, it falls under second condition again. Now if we see under second condition, we have three subconditions, just like previously. P is greater than -1, P equals to -1, P less than -1. So in this case, our P is actually greater than -1, which is nothing but 0. Therefore, T of n is equals to big O of n power log base BA into log power P plus 1 n. Therefore, the time complexity for this equation is gonna be big O of n to the power log base B A into log base 2 power P plus 1 n. Now if we substitute the value of B, A and P, then we can see that, and log base B 2 into log base 2 P plus 1, so we don't have P is 0, so log power 1 n, right? Therefore, it is gonna be big O of log base to 2 will be 1, therefore n power 1 into log base to n, which is nothing but big O of n log n. Now if you see this equation, this might look a bit similar if you have observed this clearly. This is nothing but the recurrence relation of merge sort, which is nothing but 2t of n by 2 plus big O of n, which is actually the time taken to merge. And the time complexity for merge sort is nothing but big O of n log n, which we have now calculated using Master's theorem. So this is it. Here in this video, we have majorly understood Master's theorem. It might not, you don't have to actually remember the whole theorem. You don't have to remember those formulas. It's purely just for knowledge. I am again repeating the same thing. And I mean, like, having an understanding that, such theorem exists is helpful. And it's not so important, so crucial in terms of interviews. I mean, like, it's a good thing to understand actually as a computer science student, I would say. So that's pretty much in this video. And in the next video, we'll be looking into further things like space complexity and amortized analysis. So stay tuned. Bye-bye.